Okay, so we've talked quite a bit already about standard reduction potentials and the fact that they're referenced to this arbitrary reference potential, which is the reduction of protons to water, or hydrogen gas, I mean. And that's at 0 volts arbitrarily. And so those are the E naught values, E naught meaning they are what we call a standard reduction potential for a half reaction. And it's the difference between those two standard reduction potentials that give rise to what we call full cell potential. And the full cell potential is the thing that we can relate back to thermodynamic quantities. And so I want to run through a quick example here of doing exactly that. So I've got this cell, which is copper metal reacting with iron 3 plus to produce iron 2 plus and copper 2 plus. So let's just look at this thing. You probably identify really quickly what's being oxidized and reduced. So we're going from copper 0 to copper 2 plus. So clearly that's the thing that's losing electrons in this case. And those electrons are then being dumped into the iron 3, and we're reducing iron 3 to iron 2. And since we're dumping 2 electrons for every mole of the copper, then we need 2 moles of the iron 3 to accept that, because that's just a 1 electron. So that's 1 electron each time, and that's 2 electrons each time, and that's where the 2 comes from to balance out those redox reactions. That's what we're dealing with. It's not important that you know exactly that, but let's write out these 2 half reactions first, and the goal then is going to be to compute an equilibrium constant K for this system, which is going to require us to relate ultimately the cell potential, the standard reduction potentials of each of the half cells, and then the free energy, and ultimately K for this. So sort of bringing it all together really quickly. So let's draft up the half reactions really quick. So that just looks like this, and note that I'm writing them in the directions that they are being written in the full cell reaction. So that means I'm writing copper as an oxidation step, and I'm writing iron 3 as a reduction step. I'm not writing them both as reductions, even though we're about to look up the standard reduction potential, E naught, in which case they're all written as reduction potentials. Okay, so you need a standard reduction potential list like this is by no means comprehensive. If you need a comprehensive one, you look at the back of your textbook, or the CRC handbook is what I use if you're looking for some of the more esoteric ones. We can dig these out here. These are pretty common. So we've got copper 0. Really, you've got copper 2 plus 2 electrons. That's going to be the reduction version of that, which is written here. And then we've got iron 3 going to iron 2, which should be on here. It's right there. Okay, so highlight that. So let me write these values up here. So I'm writing the values as they are in the table, which means in the reduction going direction. So for the iron 3, that's positive 0.77 volts in the reduction direction, which is the direction. So we don't need to do anything with that value. It's the copper one that we need to be careful of. Oops, and I highlighted the wrong value. It's actually this one here. This is copper 2 plus 2 electrons goes all the way to copper 0. That's the one we need, and that's 0.34. So that's 0.34, but remember this thing is, it's in the oxidation direction, but it's the reduction step. And so I'm going to have to flip this or subtract it either way, and then add these up in this direction. So what I get is my full cell reaction, which is copper 0 plus 2 iron 3 pluses proceeds to make 2 iron 2 pluses plus copper 2 plus. And if I add these two things up, it gives me plus or positive 0.432 as our E cell for this reaction. So looking at it, I would expect this to be a galvanic type reaction because of the positive sign, which means that there's a negative free energy change between those two half cells. Okay, so we have the E cell. We know it's spontaneous, and we're trying to compute what the equilibrium constant K is for the reaction. We know it's going to be greater than 1 simply because it's a spontaneous reaction. We also know that the delta G is equal to minus NFE, and I should clarify that this is E cell, which is also the same as delta E. We also know from our sort of chemical understandings of the world that the equilibrium constant for a reaction is related to delta G through this exponent of minus delta G over RT. I think I mentioned this in chapter 6 when just sort of intro to equilibrium. So these are fundamental relationships we should all know if we're chemists. So we can substitute delta G in, and we get a relationship for K, where K is equal to Euler's E, or the exponent, and that would be negative NFE. So I'll just put positive NFE because those cancel out. NFE being E cell over RT in this case. So we can take our values. So we have E cell, which we computed as this. We have F as Faraday's constant, so that's 96485. We have N, and in this case being the number of electrons, 2. And we have R. We want to be careful what R we're using for units. So this is going to be the 8.314 value, which is in units of joules per mole Kelvin, which means that our temperature needs to be in units Kelvin. So, and that's at standard. This is equilibrium, so this is implied that this is standard, and this E cell is standard. So this would be 25C, which would be the same as 298.15 Kelvin. So if you plug all those values in, what you're going to get out of this is a value that's roughly 4 times 10 to the 14, which tells you that this equilibrium lies extremely product side, and that this is of course spontaneous because of this massively positive K. So this relates us back to what we know as chemists. So we're thinking about the difference between E naught cell for a reaction versus a half reaction, and how that relates to delta G.